worries. Okay, fantastic. It's great to be back. I hope that you are all healthy and enjoying the Alps, and of course the talks, but mostly the Alps, um, and the food and so forth. I'm lactose intolerant, so I always have a bit of a rough time when I play Zeus. Um, but you know, you just have to suffer through it. The cheese is so good. You just, I mean, not eat the cheese. Um, okay, so today we're going to talk about exploring topology in circuits um, in general, and I'll also give you a bit of an intro to circuit QED at the end. Okay. Okay. So yesterday's topic, we talked about topology sort of in general, and we connected it a little bit to topology and materials. Today, I'd like to introduce you to a couple of these topological kinds of models that one can explore in circuits, classical and quantum. And hopefully that will give you a little bit more of a sense of why we were talking about the things we were talking about yesterday and what they mean, okay? Today's story is a close collaboration between my group and Dave Schuster's group. I am personally basically a cold atom experimentalist and an optical cavity QED person. And so the transmons are all developed in Dave's lab for when we integrate them into the circuits. Okay, so just a little reminder of where we're starting on this. When we put particles in a lattice, does that mean you want to ask a question, Antoine? No? Okay. Okay. Reminder, when we put a particle in a lattice and apply a magnetic field to it, the sort of figure of merit for what the magnetic field does is essentially the amount of magnetic flux that goes through each square, each plaquette of the lattice, compared to the flux quantum, which is h over e squared. Okay, and so that's some fraction of 2 pi. Okay, and so the idea we should have in mind is we're trying to build Hamiltonians like this one at the bottom and induce particles to hop around loops and build up a Aharonov-Bohm phase. And again, you'll get this same alpha no matter which of these plaquettes you hop around. And if you hop around 2 plaquettes instead of 1, you will acquire 2 alpha length phase, and so on and so forth. Okay? And that gives us all of the sort of Lorentz type physics that one can get in a lattice. Okay, so let's talk a little bit about lattice models. The lattice site for an electron is typically an atomic ion. These atomic ions have a bunch of orbitals that the electron can live in. And in some sense, each of these electronic orbitals corresponds to one band, or maybe 2, depending on how you think of it, in the lattice that the electron can hop in. The essential point is that when you bring these ions close together, their orbitals hybridize to produce the bands. Okay? Now, similarly, when we study this physics with cold atoms, we make the lattice for the atoms out of laser fields, okay? And the point is that, again, each lattice site is sort of a sinusoidal potential well, and that has a bunch of different orbitals. But if you look at just a single one of these orbitals and the copies of that orbital on adjacent lattice sites, you again build a lattice in the sense that the orbitals hybridize and the particles can hop from one site to another. But the essential point for all of this is that we're talking about sort of a single on-site orbital, usually, and hybridizing them between lattice sites to make our lattice and study our physics. So when you want to try to make a lattice for photons, you have a couple of different choices. You need some object that can hold photons, right? You need a trap, essentially. So for cold atoms, that trap is some optical potential. But one option for trapping photons is an LC circuit, okay? That circuit can trap as many photons as you want at a frequency of 1 over 2 pi root LC, okay? Another option, and so this is sort of a weird object because it's like a trap, but it only has one resonance, more or less, okay? Another option is to pick a microwave cavity, and that has a whole family of resonances that correspond to, you know, essentially different orbitals, and each of those resonances can hold as many photons as you want. So you can think of this as like the different orbitals of a single ion. Okay, and then when we couple the microwave cavities together, these orbitals couple and we get a bunch of different bands. And so again, we will typically think of a single band of this a lattice of microwave cavities, or a lattice of LC circuits. And the last option that we'll get to at the end is to make a lattice of capacitively shunted Josephson junctions. And these sort of act like LC circuits. And so once again, they have a single orbital, if you will. They can take photons with one spatial wave function. And then we'll try to couple photons between them and make lattices. And so we're going to talk actually briefly about each of these three platforms. And we'll go from there. So before we even hop into the platforms, though, I want to make one more comment, which is that breaking time reversal symmetry is hard, okay? The way you should think about this is that we will need to generate tunneling phases such that when our photon hops from one lattice site to another, it picks up a phase associated with that hop, right? And so the point is that the wave function of the electron or the photon or the atom is a scalar quantity. And so we can multiply that wave function by a number or by a phase, and that's this complex tunneling phase. So there are ways to engineer that directly, but they're a little tricky. The simplest option is to, instead of having a complex scalar field on each site, to have a real vector field. That is to say, to have a real spatial spin or pseudo spin. That is to say, 2 degrees of freedom. They need not be spatial, right? You could have 2 resonators on a site if you wanted, and you could call one of them X and the other one Y, okay? And then if you can rotate that vector when you go from one site to another, something that implements that geometrical rotation, that effectively gives you models that behave the same way or seem to behave the same way without actually having to break time reversal symmetry. And the point is now that if you actually go through the math, it'll give you 2 copies of the model. One that experiences a magnetic field in one direction, and one that experiences a magnetic field in the opposite direction. And as long as you don't induce coupling between those 2 models, you will be good to go to explore this topological physics. And this is actually something that one studies in what are called Z2 topological insulators, where for electrons, what people observe effectively is that UPS electron spins, here it's really an electron spin, the up spin experiences a magnetic field out of the board and has cyclotron orbits in this direction, and the down spin experiences a magnetic field into the board and undergoes cyclotron orbits in the opposite direction, okay? And the way that one gets this in a real material is through spin-orbit coupling, which we think of as something that happens in a single atom, right? But it turns out when you couple atoms together, the sort of local angular momentum around the nucleus of that atom, which is coupled to the spin, becomes the orbital angular momentum in space. this electron moving around. So again, this is all just words for now. We would like to try to implement this physics in a circuit. So let me show you what I mean, okay? Previously, we talked about a phase, right? But you could imagine having a spatial vector associated with your particle. And so when I hop to the next site, if I hop vertically, I pick up no rotation. But if I hop horizontally, I get a 90-degree rotation, right? For some total, almost 90-degree rotation. Okay? And so the upshot here is that you've rotated a spatial vector. You haven't rotated a phase, but maybe they're the same thing, okay? And so we'll see that they sort of qualitatively are. So this kind of idea has been explored with optical photons a fair bit in waveguide arrays and cavity arrays. And in fact, the time reversal broken version has been explored in ferromagnetic materials. And we'll talk more about that shortly. Okay, so the topological circuit that I'm going to show you and tell you about now is this is from this Physical Review X paper. And we think about this topology stuff as being extremely quantum mechanical in nature. What I would like to argue to you is that you can literally study it on a printed circuit board. Okay, this is just an FR4 printed circuit board. Each of these blue objects is a capacitor, okay? And each of the black objects is a relatively high Q inductor, okay? So topological physics is not fundamentally quantum mechanical. There are quantum mechanical aspects, right? But we're just gonna study here a wave equation in a circuit. Okay, so what is the idea? Imagine for a moment that this right here is one lattice site, okay? So my photon can live in an LC circuit on this purple inductor or on an LC circuit in this red inductor, okay? So we're going to imagine these two LC resonators have the same frequency, okay? And then the idea will be, I'll call the amount of excitation in the purple one the amount of excitation in the Y direction, and the amount of excitation in the red one to be the amount of excitation in the X direction, okay? And so now I can couple these lattice sites to one another with capacitors, okay? So if I couple the red LC circuit on this site to the red LC circuit on the next site, the X component gets converted on one site, gets converted into the X component on the next site, okay? And similarly for Y. And I can do the same thing for this pair of sites, okay? So I've converted X to X and Y to Y, and then again X to X and Y to Y. But then I can do something interesting. I can convert the X excitation on this site through these capacitors into a Y excitation on the lower left side, okay? And I can also convert the Y excitation on this site into minus the X excitation. Notice I've flipped the sides of the inductor that are coupled together through these capacitors, right? And that converts X to minus Y, okay? And so what this is really doing, I'm taking a vector, okay? I convert X to Y and Y to minus X. And then I go the last step and convert X to X and Y to Y. And so in total, this has implemented a 90-degree rotation of my vector, right? In a sense, I've made a matrix where the total matrix takes X to Y and Y to minus X. So that's a matrix of 0, 1, minus 1, 0, which is just a 90-degree rotation matrix. Okay? So this is quite interesting because we can now extend this to make our whole lattice. Because remember, a 90-degree rotation matrix is in some sense a phase rotation of pi over 2. Okay? And so instead of drawing out all those crazy couplings, what you can see that I've done here basically is drawn it as these phase rotators. This object does nothing. This one rotates by pi over 2, right? Pi over 2 is x to y and y to minus x. This one rotates by pi, which is x to minus x and y to minus y. And this one rotates by 3 pi over 2, which is x to minus y and y to x. Okay? And so literally just by kind of braiding these couplings, we can have a situation where the vector is rotated through whatever angle we want in going around a loop. Okay? And so here's the interesting thing. If we call an excitation on the red one A and the excitation on the blue one B, a 90-degree rotation does not leave excitations in either A or B. A and B are no longer eigenstates of this system, right? In fact, the eigenstates are A plus or minus IB, right? And when I go through this loop, if I call A plus IB my up state, up will become e to the I pi over 2 up, and down will become e to the minus I pi over 2 down, okay? Which is to say, under rotations, the eigenstates of rotation are circularly sort of polarized, if you will, right? Not linearly polarized. So before we move forward, does it make sense why this now creates two copies of this sort of Hofstadter model? One copy for upspins, which experience a rotation of a phase of pi over 2, a flux of pi over 2 per plaquette, and another one for the downspin that experience a flux of minus pi over 2 per plaquette. Does that make sense to everybody? Can I move forward? So much silence. Did you not give them coffee during the break, Antoine? Okay. Okay. Onwards. So we can build this whole lattice of these things. I showed you what the lattice looks like. And you can then compute a band structure. Okay? So here's the first question for you. I guess I maybe shouldn't have shown you the answer first. But how many sites are there in a unit cell for this lattice? Where a site is a pair. This two inductors is two LCs is a lattice site. So there are two ways to see that. One way to see it is that if you go back here for a moment, you can see that literally, physically, we've had to engineer couplers that are different, right? And when you get down to the next row here, right, the next one will be a phase of 2 pi, which is literally physically the same connections as a phase of 0, right? Another way to see it is that I labeled this unit cell, and there are 4 of them in there. And I assume that you're all graduate students, and at least in the US, you have to be able to count before you can get your bachelor's degree. So I don't know how it works in Europe, but I assume it's similar. Okay. So another way to see it is that there are, in fact, 4 bands here, shown in gray. 1, 2, 3, 4. Okay. So these are the sort of 4 bands of this lattice. And so the idea that you should have in mind now is that photons in this lattice, in the bulk, will sort of stay localized, okay? And on the edge, they should be able to move around in space, okay? But it will be chiral. They'll only be able to move in one direction because of this sort of chirality of the hopping, okay? Now, the interesting point here is that when we told this story in the continuum, I kind of said, well, any size orbit is going to be allowed, right? any size orbit will have the same frequency, right? But you can pick the size that you want, the radius that you want. But that sort of ignored the wave property of the electrons, right? There's some energy momentum uncertainty, if you will, or equivalently, if you compute the Landau levels, they have some length scale associated with them. And here we have so much magnetic field, right? A magnetic field of pi over 2 per plaquette, right, corresponds to like thousands of Teslas in a solid state material, okay? Because the idea is to get a flux quantum through, you know, a nanometer by nanometer square, you have to have a huge field. So we can study this in this circuit because, of course, we're not using real magnetic fields. But the magnetic field is so huge now that you kind of start to see aliasing kinds of effects. It's like if you try to draw a circle on your screen, but you don't have a retina display, and you make the circle on the order of the size of your pixels, you can see that the orbits kind of get a little bit quantized and pixely. So here what we're going to see is that these edge states are effectively 1 or 2 lattice sites wide, okay? So how do we see this? Well, what we're going to do to understand this stuff, if you wanted to do the math, is do a full calculation of the behavior of the circuit. I've written here that it's not a tight binding model, and that's another subtlety that if you want to ask about at the end, I can tell you about it. It's quite interesting, but it's not central to our understanding for right now. So the basic idea is we take a network analyzer. Let me ask again, how many of you are theorists and how many experimentalists? Who's a theorist? Are you all theorists? Are there any experimentalists there? Oh, it's like 50-50. Okay, good. Okay, terrific. I don't have anything against theorists. I was just about to say the word network analyzer, and I realized that if we're all theorists, maybe that won't mean anything to you. But the basic idea here is the following. You can inject a signal into a particular lattice site in this circuit just by putting a little magnetic coil above one of these inductors and coupling to it inductively, okay? And then you can measure a signal at another lattice site with another coil, okay? And sometimes we do one inductor, sometimes we excite a pair of inductors with the appropriate phase to excite a particular spin state, okay? But the picture you should have in mind now is we can really make a scanning, tunneling kind of microscope to see the microscopic behavior of the system. And so the point is, if we excite at a couple of points in the bulk of this lattice, say we excite here and we measure there, what we see is that so the red is the theory, the blue is the data. What we see essentially is that there are these regions where you can't excite the system at all, where effectively it doesn't conduct, if you will, though these are bosons. Okay, and so these are the gaps between the bands. If, on the other hand, we excite and measure at 2 points on the edge of the system, we get a very strong response within these gaps. And now we can actually look in real space at the response at this frequency, okay? If we excite in the bulk, we get this exponentially localized response, which is sort of the discretized version of a cyclotron orbit, okay? If we excite on the edge, we excite an edge mode at a particular momentum, okay? So this is in the frequency domain. We can now do something similar in the time domain. So what we're gonna do is send a pulse in to one of the 2 spin states in this gap between the bands, okay? And watch the response in real time. So this is actual data, okay? And what you see is that the excitation goes around the edge of the system. And you can sort of unwrap this and look versus site and versus time and watch the edge states propagate around in one direction, okay? And in fact, if you excite both spin states by just exciting one inductor, you can see the two different spin states propagate in opposite directions. This is a spin resolved readout as well. Okay, so this works very, very nicely. You can actually see the corners here very clearly in the data, because while there's topological protection against backscattering, right, nothing prevents you from changing the dispersion of your lattice near a corner, right? That doesn't backscatter, but it does distort your pulses. And so that's what's going on at these corner sites. So this gap is topologically protected. It turns out this one is not, because there's no band above it. And so if you excite here and measure the response, you just get garbage, kind of as you expect. Okay, but now we can do some really crazy things as well, because this is made in a circuit. Okay, we can engineer non-local couplings. So we can couple one edge of the system to the opposite edge of the system just with wires. No problem, works great, okay? And so you can now study this kind of topological physics on a Mobius strip, for example. So here we've not only connected one edge to the other, we've also added a twist, okay? And so when we do that, what we see is that the excitation goes around the edge and then appears on the other edge in the opposite spin state and then comes back to the first edge, okay? So this all works just exactly as you would expect. And unless you believe that this is kind of somehow unique to these sort of spin Hall models, you can actually build almost any topological model you want. Another very popular model that people are very interested in is studying these Weyl semimetals, where electrons exhibit a linear dispersion in 3D, okay? And the point is that to really make a linear dispersion in 3D without having to have some kind of discontinuity in your in your dispersion relation, to have a nice linear equation with a linear dispersion, the simplest thing is to dot the momentum into the spin of the particle. Okay, and so people have seen this in ARPIS for electrons. There are now experiments studying this kind of physics with microwaves. And so our point was just that you can also make this, in addition to these sorts of systems, in a circuit. So what's the idea? It turns out that there's a beautiful paper from Wolfgang Ketterle's group, designed for cold atoms, actually, initially, where the idea is just that if you have pi flux through each of the three real space surfaces, you get 4 Weyl points in the Brillouin zone, okay? And so literally all you have to do is engineer a circuit such that when you hop around a plaquette in any of the 3 dimensions, you get pi flux, okay? So how did you do that? It's actually quite straightforward. Our inductors are shown here. So this is the 3D structure of the lattice. And then the point is, for each of the plaquettes, we just flip the connectivity for one of the 4 couplings. Okay? So one of the 4 in this direction, one of the 4 in that direction, and one of the 4 in the other direction. So you kind of run through what this is going to look like. Actually, and I think in this plane, it's actually 3 of the 4, which is the same as 1 of the 4. So this is what it ends up looking like in terms of the connectivity. And now, instead of needing one printed circuit board with inductors and capacitors, you guessed it, if you want a 10 by 10 by 10 lattice, you need 10 printed circuit boards. So these are hand assembled. And if you wonder why we didn't do this sooner, it's because we really didn't want to solder together all these boards. But eventually it kind of became too irresistible to do. And we had a visiting student, actually a really wonderful guy, Leon Liu, who's now at Berkeley. he spent a little bit of time on circuits and then decided he'd rather do cold atoms. I can't imagine why. But anyway, you solder together these 10 printed circuit boards. And then this is a movie of what the measurement process looks like. Okay, so literally what we have here is a scanning tunneling microscope, essentially, with these 10 by 10 by 10 lattice. And we've destroyed a 3D printer and replaced the print head with an inductor to measure. Okay, and then you collect the data on this network analyzer. So anyway, you can do this, and then you can actually measure the spectrum of this thing. This is real data, and you can see that basically when you look versus frequency, you get eigenstates that form spheres that get smaller and smaller and smaller as you approach the energy of the vial point, and then grow again on the other side. So we can really see these vial points, and we can even see in fact, the spin texture is exactly what you expect for that is to say, it points into some of the vial points and out from other ones. Okay, and then there's some additional physics which I won't talk too much about beyond mentioning. For those of you who know about the surface states of vial systems, in fact, on each of the surfaces of one of these systems, you get Fermi arcs that are connected in sort of bizarre and exotic ways. So these are the Fermi arcs of the system. Okay, so that's the extent of that story. We've kind of, I hope I've given you a flavor of how you engineer this connectivity with a real space rotation. And what I'd like to talk to you about next is how to actually break time reversal symmetry in a topological circuit. And here we'll do it in an array of microwave cavities. So this should give you a flavor of basically how to make lattices for microwave photons and how to actually engineer a real honest-to-God time reversal breaking Berry fix. But before we go on, are there questions on this piece? Okay, so the sort of second third of this story, although the last third will be very, very brief, the second third is about making arrays of microwave resonators and coupling them together, okay? So how do we make a microwave resonator? Well, the microwave resonator I drew for you was actually a closed box earlier. And of course, that will have a whole bunch of resonances. And then you could couple those boxes together by drilling holes, okay? And this would work great in principle. The size of the hole would determine the amount of tunnel coupling that you have between the sites in your lattice, okay? The downside to this approach is it's then very hard to probe the lattice. And as we'll see, it's also hard to break time reversal symmetry, right? Because if you've got closed boxes, how do you probe them? And kind of eventually we need to get something in them to engineer interactions and so forth. So it's not ideal. But there's another way to make microwave resonators, which was popularized by Rob Shulkoff's group in this paper I've listed here at the bottom. And the basic idea is what I've drawn here. So this is a wild object because you can get Qs in the hundreds of millions basically without putting a lid on this box. So that should make you very uncomfortable because normally the point is that the Q comes about because the photon can't leak out of the box, right? So why can't the photon leak out of this box? Well, the basic idea is that whenever you have a waveguide without a center pin, that waveguide has a low frequency cutoff. And photons that are below the frequency of that cutoff can't propagate in the waveguide. And so what we've done here, if say we want to operate at 5 gigahertz, essentially what you have to do is make this tube smaller in diameter than a quarter of the wavelength at 5 gigahertz. And then what you get is an exponential suppression of propagation. Basically, the light just can't propagate down this waveguide. okay? And then what we need to do is make a 5 gigahertz resonator at the bottom of this tube, okay? And so the way you should think about this 5 gigahertz resonator is we've added a center pin. So this bottom piece here is basically like a coaxial cable, okay? Where, you know, coaxial cables are happy to propagate light whose frequency is well below the spacing between the center pin and the outer shield, basically because the signal can propagate on the center pin, okay? And so now you should think about this as a coaxial resonator waveguide where the center pin is shorted to the shield at one end and open at the other end, okay? And so this object is a quarter wave resonator, which means that you can put a quarter of a wave in, you can put 3/4 of a wave in, you can put 1 1/4 waves in, so forth, okay? And so what we do is we make this a quarter of a wavelength long, and then we make sure the diameter is less than, I'm not sure if it's half or quarter wavelength. But what you find in the end is now you can make this mode that has a node here and an antinode there, and then can't leak out of this tube, okay? And so, you know, the best number for a while for this kind of thing was like 170 million for the Q. I think people have seen 500 million now at millikelvin temperatures, or even billions. So in practice, literally what you do is take a block of aluminum and machine a hole into it and leave a little post in the middle, okay? So that's what you get if you have a uniform cavity. What we can now do is put 3 posts into this cavity, okay? Why do I want to put 3 posts in? Well, if I put 3 posts in, you can think of this as essentially like 3 coaxial resonators that are coupled together, okay? And this is quite neat because this is like a 3-site lattice with tunneling between the sites, kind of given by the separation between the posts. And now we have something that's very weird. What's weird about this? Well, of course, we just get 3 modes, right, that are just at 3 different quasi-momenta, one at quasi-momentum 0, one at quasi-momentum 2 pi over 3, and one at quasi-momentum minus 2 pi over 3. And so that kind of determines whether all 3 electric fields are oscillating in phase or the excitations are going in one direction or the other. But what we can now do to separate the energies between the ones where the excitations go in one direction and the other direction to induce a sort of spin-orbit coupling, for those of you who like to think in that language, is put a ferry magnet into this cavity and apply a magnetic field to that ferry magnet. And so the point basically is that one of these modes generates a magnetic field that rotates with the ferry magnet and can then hybridize with the ferry magnet and get split in energy. And then the other mode is basically left alone. So this leaves us with a very bizarre thing where we have this isolated chiral mode of this cavity. Okay, so we now know how to make 2 ingredients. One is on-site spin-orbit coupling, okay, and the other ingredient is just a lattice site. So imagine we now want to couple these lattice sites together. Well, all we have to do is drill a hole to couple them that's narrow enough that the microwave photons can't leak out into free space, okay? So this is now a neat thing because now we know both how to make lattice sites and how to couple them together. And the deeper we make this cut, the more coupling we have between our sites, okay? And it's all open optically, so we can see in, we can potentially put probes in, but basically for microwaves, it's very well contained, okay? So we've got our ingredients here. We've got the couplers and we've got this spin-orbit coupling. And so now what we can do is couple these sites together. So the sites with nothing in them are just the bare lattice sites with a single post, okay? And we've tuned all of them to the same energy. The lines are these holes drilled between the sites that allow the photons to hop from one site to another. And these chiral objects are these spin orbit coupled sites where that single mode, where the mode goes, with a given chirality is tuned to resonance with the adjacent sites. So this is very interesting. Why? Because remember, I told you that that mode had a quasi-momentum of 2 pi over 3. So what that means, effectively, there are 3 posts. And so what that means is when I go once around the cavity, I pick up 2 pi of phase, 0 pi over 2, 3 pi, 3 pi over 2, 2 pi, okay? So when I hop in here and then hop out there, I pick up a phase of 3 pi over 2 because the on-site orbital has that phase of 3 pi over 2 associated with it, okay? And now we can start to understand how spin-orbit coupling in a solid gives rise to a Peierls phase in an electronic material. The point is, when an electron hops from one ion to another ion, and then to another ion, the point is the orbital, the part of the orbital that couples to these different ions has different phases. And so consequently, you pick up a Peierls phase when you go around a loop. Okay, so anyway, this circuit again gives us a Peierls phase of pi over 2, but there's no copy at minus pi over 2, or actually there is, but it's tuned away in energy because the YIG split out. YIG is a yttrium iron garnet. That was that little sphere in the middle of the cavity. Split that mode out in energy. Okay, so this is what this thing looks like when you zoom in. You can see the 3 posts. You can see the little YIG spheres in the middle. You can see my thumb there for scale. You can compute the modes of this object. And again, the mode structure looks very similar to what we drew before, except we have these additional 2 objects above and below. And these come from those modes that go in the wrong direction that are coupled to the yttrium iron garnet sphere. And so we just completely ignore those. And again, we can measure the full band structure of this thing. So we've superimposed the computed band structure on top of the measured spectrum with a network analyzer. And you can see all of the structure that we expect, including edge states. You can look at dynamics in this kind of a system. You can see the photons go around the edges. What I'm showing you here is data at room temperature. And so the photon makes it maybe once or twice around the system. The next thing we did was make it cryogenic, basically put it at millikelvin temperatures. And you go from once or twice around to, we got bored. We didn't, I mean, it just goes around basically forever once you make the thing superconducting. So it just, it really works like gangbusters. And you can use this for the topological physics in a similar way to what I showed you before. Okay, and the last ingredient for studying sort of few to many body physics in circuits is adding interactions. And so the story here, time permitting, is that one can make a mod insulator of microwave photons. But in fact, I think unless people are really curious about that, I will probably just tell you about how one makes the ingredients to make the photons interact, rather than going through the whole mod insulator story, because this is supposed to be a talk on topology. And yes, I know the string order is topological for mod insulators, but we haven't measured the string order. So, okay, so how does one make photons interact with one another? Of course, the point is that fundamentally, microwave photons or any photons don't interact until you look at a high order in perturbation theory and quantum field theory, where basically the photons can turn into electron-positron pairs that then interact with each other. But that process basically has a very, very tiny cross-section such that it's ignorable, okay? So to make the microwave photons interact with each other, we have to hybridize them with matter in some way, okay? So what does that look like? Well, first of all, what does an interaction even really mean here? We've made our LC resonators, right? And I told you they have a single mode, and that single mode can have as many photons in it as you want. Okay, that's our kind of box. And if we put this resonator at 4.5 gigahertz, well, you put one photon in, it's 4.5 gigahertz. Put another photon in, it's 4.5 gigahertz. And on and on and on, as many as you want. Now, that's not quite true, right? If I put enough photons into this LC circuit, the resistance of the inductor would heat up the inductor, right? And when the inductor heats up, it probably expands. And when the inductor expands, its inductance changes. Yes? So if the inductance of the inductor changes, the frequency of this LC circuit changes. And so this is kind of a neat thing, because fundamentally it says that eventually this spectrum will become anharmonic in the number of photons that you have in the system, right? But that anharmonicity is very, very small, and it depends on the resistance of the inductor. So this is a lossy process. It's kind of a mess. Well, you say, in fact, there's another process, which is what one might call optomechanics. And the idea there is that the current flowing through the inductor produces a magnetic field, right? And that magnetic field backacts on the electrons flowing in the inductor and just directly applies a mechanical force to the inductor, which can change its size as well, right? So people do optomechanics experiments. That's absolutely true. But again, to make that effect large enough that, you know, it makes this spectrum anharmonic and makes your photons interact with each other strongly is difficult to do. What one can do instead is put in a Josephson junction as this nonlinear inductor, okay? So this is just basically aluminum and then aluminum oxide and then another layer of aluminum. So more or less what you do is you deposit aluminum on silicon, and then you expose the thing to air, and then you deposit more aluminum on top of the first layer of aluminum. So you've got like a nanometer thick tunnel barrier there. And what that effectively creates is a nonlinear inductor, okay? But it's extremely nonlinear. And so the point is that if the first photon that you put into this Josephson junction capacitor resonator has a frequency of 4.5 gigahertz, then when you try to put a second photon in, this Josephson junction is so nonlinear that the frequency of that second photon going in there is 4.2 gigahertz, okay? And so the way we think about this, if you think about this as just a site in your lattice, putting two particles in costs 300 megahertz less than twice putting one particle in, okay? So that means we have a 300 megahertz attractive interaction between our photons, okay? Now, I should say this technique was actually developed by Dave Schuster and Rob Shulkoff in the early 2000s. And their idea initially was to use it for quantum computing. The basic point being, this 300 megahertz anharmonicity is large enough to essentially isolate the lowest two states, 0 photons and 1 photon in the LC circuit as a two-level system. Okay, and so you can use that as the core of a quantum computer. This is more or less what Google uses for quantum computing. Okay, these Josephson junction capacitor qubits, they call them, or transmons or xmons or gmons. They have all kinds of patent pending names for them. But the important point is that if you have physics that can probe this 2-photon level and you see that there's an interaction here, that there's a shift here, you can now think of this as like the Hubbard U in your lattice, okay? And so the cool next trick here is, okay, this makes one lattice site, and you can now couple them together with capacitors. And depending on the strength of that capacitive coupling, you can induce hopping between your lattice sites, okay, of any strength that you want. So the numbers you should now have in mind are a 300 megahertz attractive interaction. 10 megahertz tunneling is pretty normal, but you can make it whatever you want. And the photons in one of these Josephson junction capacitor resonators have a lifetime of 40 microseconds to now people have seen up to like 500 microseconds. And so what this means is that you should really think about the product of the lifetime in the interaction. That tells you kind of how many collisions you can get. And so a typical number here is like 12,000 collisions, okay? And that's quite similar to the Hubbard U for cold atoms, which is like a kilohertz maybe, times the lifetime of a cold atom in an optical lattice, which is maybe a few seconds, right? So again, it's thousands to tens of thousands. So even though this lifetime looks fairly short, right, when you put these into unitless quantities, you get similar kinds of numbers. And it really does suggest that you can start to study many-body physics in these circuits. So I will just flash up the result here, which is that you can really make a mod insulator of photons in this kind of a system. You can read out the occupation of the individual lattice sites. You can see Rabi oscillations as particles coherently hop back and forth between sites. And finally, you can play games like filling a system up. So this is sort of, we played some games in non-equilibrium thermodynamics where we add a chemical potential to this system and fill the system up to 1 particle per site. You make a mod insulator. I should also mention these same kinds of techniques have been used by Pedram Roshan and colleagues at Google to start to study things like many-body localization in the few particle sector of a similar Bose-Hubbard lattice. So I've zipped through a ton of stuff here, but I wanted to leave a lot of time for us to just chat today because I got feedback that I didn't leave nearly enough last time. And when I say I didn't leave nearly enough, I mean I left negative 10 minutes. So this time I have left 4 minutes. So let's chat. Yeah, so what things can I tell you there for certain? We can go back. So some of the features that people are interested in, which is the data I want to show here. I guess I don't even want to show data. I want to show a theory plot. Where is it? Here we go. So you can see here that even in the theory, there are 4 bands. So this is just a Harper-Hofstadter model. It has 4 bands, but 2 of the bands touch. And it turns out that these band touching points are Dirac points, which are 2-dimensional points where you have essentially a P dot S interaction or a P dot sigma interaction. So this has a Berry phase associated with it. And then you have these 2 gaps, right, where we have topologically protected edge states. So one question that you might ask is, what sorts of models give you Dirac points, right? And I think the point is you have to have something that has an inversion symmetry to get a Dirac point. And so an inversion symmetry means that there sort of have to be 2 equivalent kinds of sites. And so what that means is that the phase needs to be a rational fraction of pi, not a rational fraction of 2 pi. Okay, so for example, Liang Jiang came up with a really cool way to design a circuit that gives you a phase of 2 pi over 3 instead of a phase of pi over 2, right? And essentially what he does is he has a design with 3 inductors per unit site instead of 2 inductors per unit site, and then braids their couplings in a sort of non-trivial way. And that one has 3 bands, it has bigger gaps, and it doesn't have a Dirac point. Okay, and so I guess inversion symmetry is one argument. What other interesting features are there that one might want to get other than a topologically protected edge state or a Dirac point? In 2D, I would say that's about it. In 3D, you can produce these Weyl points. And it's a very interesting question. Why does one get a Weyl point by getting a phase of pi along each of the three axes? And I don't think I have a really great argument for that. What I can say is that Jacopo Carusotto has been trying to convince us to make a 4D lattice. And he claims that there are some other additional exotic features that appear there. The problem to me is that a 4D lattice would require essentially making 10 of those 3D lattices. And I don't think there's anyone on the planet who has that kind of patience. If you know someone, send them my way. But yeah, I'm not sure if there actually are even other interesting features that one can make there. I have to say, speaking for myself, some of what's happened is this linear physics, I think, is fascinating in that it teaches you what's possible, and that fundamentally, without interactions between the particles, all of the topological stuff is classical, right? But I think the whole zoology of these things, it's not totally clear how much further one wants to / ought to go on that beyond simulating it, right? Unless there are additional open questions, and I'm not totally sure what they might be. This slide? One, two, three, four of these. Yes. And you can also see that this is a much smaller lattice. It's a good question. Do we see them in the room temperature? So I think probably, actually, honestly, what the difference is at room temperature, you can basically, it's easier to manipulate how you're putting the probes into and out of the cavities, right? So in fact, what's likely actually going on is that in the cryogenic system, you don't really have the control to make sure that you're coupled to all of the lattice sites equally well, right? You might put it in and get them approximately equally coupled, but then when it cools down, who the heck knows what happens, right? So you can kind of see there's some non-uniformity amongst all of the couplings. So my guess is really that that's what it is. And yes, in retrospect, there are some really neat sum rules that you can use to extract your coupling strength. And so we can talk about that later if you'd like. Basically, the point is, if you measure the strength of the reflection and integrate over all frequencies, the complex reflection, that gives you your coupling strength, right? This is sort of a provably true thing from some rules, even when there's a whole family of modes that you're coupling into. And so one could use that to fix this and see how strong this corner effect really is. But as I think about it now, I don't think it's actually corners. I think it's just that the couplings are non-uniform. Yeah, so this system is only like 5 by 5. So there's not that much difference between the bulk and the edge, right? Essentially, the way to think about it is that if you have enough disorder to couple one edge to the other, it's bad, right? And this is a fairly low disorder lattice, so that's not a concern. The localization length of the edge, I think, is like 1 or 2 sites. So there's very little extending into the bulk of this thing anyway. I think an interesting question is when you start to make these systems strongly interacting, and I guess I can also show that data. We've coupled 1 qubit to this Chern lattice that I'm showing here, and we can count photons in the edge modes and these sorts of things. Once you have interactions, the edge states will actually be in a different phase of matter than the bulk, and so it can be fairly important to not have edges in your system. And so this is another thing that's actually quite neat about the circuits. If you follow all of these works from like Alicia Coyar, who's studying hyperbolic lattices or flat band lattices, basically the point is we can really engineer arbitrary connectivities or near arbitrary. And so the idea will be to completely get rid of the edges, right? Like literally add a coupler to the system that couples one edge to the other in sort of a toroidal configuration. So the system is all bulk. There's no edge at all. And then you can really sort of study fractional quantum Hall physics on a torus, which is where it's nicest and easiest to understand. We can also talk about the stuff from yesterday. If people had questions about yesterday's material, I'm happy to revisit that. Uh-huh. Mm-hmm. Yeah, no, this is a really fun question. So the way to think about this, so part of the answer is I don't remember what the number is off the top of my head for the 3-body term compared to the 2-body term. I think, but one can compute it fairly straightforwardly. For those who are interested in knowing how to compute things about transmons, the best place to look, in my opinion, is Dave Schuster's thesis. It turns out the basic point is that a transmon qubit, because it's a capacitor and a Josephson junction, the Josephson junction has a response which goes like or an energy which goes like the cosine of the phase between the two sides of the junction. And the capacitor gives you an energy which goes like the phase squared. Okay, so actually this is kind of an instructive thing. Is somebody else giving a tutorial on circuit QED? Okay, so you'll learn about this stuff anyway. The basic point is that the Hamiltonian for a single transmon looks like phi squared plus cosine phi, right? And so the point is that essentially a single transmon has the same spectrum as the bands of an optical lattice, right? Where phi replaces your position coordinate, okay? And so the essential key is that you need to make the lowest band flat enough that all of the states in that band have essentially the same energy so that you're not sensitive to charge noise, okay? And then the spacing between the bands is the n-harmonicity. or essentially your 2 or 3 body term. So my guess is that it's, the energy is 5 gigahertz, the 2 body term is 300 megahertz, so the 3 body term is probably 20 megahertz or something. Would be my naive guess. And does that affect the physics? I think it depends what physics you're trying to study. Like for many of these fractional quantum Hall type phases, the competition between having quasi-holes in a nu equals 1/4 Laughlin state and having a nu equals, or excuse me, having quasi-holes in a nu equals 1/2 or having a nu equals 1/4, the relative preference between those two can be set by a 2-body term, or a 3-body term rather, right? It's set by microscopics. And so by playing with the strength of the relative strengths of those terms, you can affect the phase diagram. So this is kind of like saying, if you look at the plateaus that one observes in the conductance for the fractional quantum Hall, how wide are those different plateaus? That ends up being stabilized by the higher orbital terms. The locations of the plateaus and the fact that they are locally flat is topological, right? But where they are, and how wide they are, is set by microscopics. So that's sort of my sense on where that could potentially be interesting in the topological sector, right? But people like Andrew Daly also have proposals to study things like pair superfluidity in Bose-Hubbard models, stabilized by 3-body interactions, right? So one could imagine just directly studying that kind of physics in these models as well. But that's not topological. Everybody's happy, or either everybody's happy or everybody's sad. It's just a position. My pleasure. I'll see you all tomorrow. Bye bye. Ciao.